Hello. So now we are on question 2, and I apologize first. It's wrong. So I don't know why, but I thought the least squares estimator and GMM are different. But after a very long and dirty, tedious algebra, I find they are the same. Maybe when I make this question like 2 years ago, I did a algebra mistake. So, but somehow students like answered they are different. So maybe I was wrong and students believed it. But this year I find my mistake. I don't know where what the mistake was, but I find the problem is wrong. So first of all, I'm telling you the idea why I thought uh, they are different because the least squares estimator minimizes this guy, right, or its simple counterpart, and it implies the first order condition this way. Again, I have to say beta 0 here, so my notation is not like rigorously correct here, but okay, please pardon me. It's my so but my intention is not it's in this statement beta is not our focus. We are not going to consider beta, but what I want to tell you here is there is only one dimension, one the first condition is just one uh, equation. That's what I wanted to say. So this as an equation, so something equals to 0 is just one equation, but the GMM relies on this and this, right? So I have to say this in here too. So this is satisfied when beta equals to beta 0, right? And another, so this is an additional exogenate assumption which is not utilized in the least squares. That's what I wanted to show you here, and that's why I thought they are different. But after just standard derivation, so derivative and variance, and then also we have to define uh, annoying notation like this, and a very annoying notation after annoying processes. We define optimal weighting matrix like this. By the way, I'm going to like comment on this. So we know the variance of the moment function takes this form, and here sigma squared is the variance of epsilon under homoscedasticity assumption. So you have to do this, but by the way, so in theory, the optimal weighting matrix is omega inverse. That is right. But more rigorously, a weighting matrix is optimal as long as it is proportional. Like sigma squared is not a problem at all. What you need here, because it is multiplied to every equation. Basically, the main idea is we have two moment conditions for one parameter. So we have to allocate weights across two moment functions, but sigma squared is multiplied to both of them. So it does not affect the weight, right? What matters here is the distribution of these guys, how you allocate values of over two different equations. So anyhow, no matter what you multiply, as long as you multiply the same number to both equations, it won't matter at all. So you don't need to have it. We will simply ignore sigma squared. But this part matters because this part differentiates the two equations. Treat two equations differently by this 2 by 2 matrix. So invert the 2 by 2 matrix here. So we have a valid weighting matrix, optimal weighting matrix. again, this is what I wanted to say here. By the way, you have to mention this again in your answer. If you write this and write this without saying that, you are like there is a missing step. So, like, if you don't understand what I'm saying, just include sigma squared. But like, so put it this way: among correct approaches, the worst is estimating sigma squared and estimating the weighting matrix using sigma squared estimator. And then a better approach than that is ignoring sigma squared, because you don't need to do that. And then in some cases, we learned from here, weighting matrix does not matter under certain conditions. If the conditions are satisfied, you don't need to calculate any weighting matrix. So there are different degrees of like cleverness, how you minimize efficiently do the estimator. But if you are not certain, just do the full steps, because everything else is wrong, right? And if you don't understand what is wrong, what is correct, then just take the most safe one, including sigma squared. But if you have enough understanding to go to distinguish, to see what it means, then like understand it as a way to make it efficient. Like, I mean, save your work. Anyhow, the first condition then becomes this, and from here we have to do algebra. So maybe when I made this question, I tried myself this algebra. You have to calculate this and then take inverse of that and do the dirty job. And here you can stop the video and see if it's correct. I did it by myself. It still may be wrong, but it looks correct. So please check me. And also, this is the second part, right? Second part can be derived this way. And then as a result, we have this, which is the least squares estimator. This is GMM result, but happens to be the same as the least squares. I don't have a good intuition yet. I don't know why suddenly the GMM becomes the same least squares estimator, which relies only on one moment condition. So we'll think about that. And I'm sorry about my mistake. Okay, I will finish it here and moving to question 3 in the next video.